Hello and welcome to lesson 34 of this introduction to calculus with Wolfram U. The topic for this lesson is logarithmic functions. So let's begin with a brief overview of the subject. In the last lesson we talked about exponential functions like this one, 2 raised to x. So here is a plot of the function. The question is, suppose we want to solve the equation 2 raised to x equal to 5. The problem here is that 5 is not a power of 2 in any obvious way, so we give it to solve, and then solve comes back and tells us that x is logarithm 5 or logarithm of 2. So that's the answer given by solve, and really speaking it's the logarithm of 5 to the base 2. So that's an example of a logarithm. So this lesson will talk about these logarithmic functions in more detail and some of their properties. So basically, a logarithm is an inverse function because it is the inverse of an exponential function a raised to x. So you can think of it as having the property that a raised to the logarithm of x to the base a is x, and so is the logarithm of a raised to x to the base a. So the number a is the base of the logarithm. Now we have a function called log in the Wolfram language which does these calculations. So the log of 27 to the base 3 is 3 because 3 raised to power 3 is 27, and the logarithm of a quarter to the base 2 is negative 2. But keep in mind that the default base for log is e. So the logarithm of e square is just 2. So that's the natural logarithm which is implemented in the Wolfram language with base e. Next, let's take the graph of the logarithm function. So here's the graph, and you notice that it's defined only for positive x, and the range is all the way from negative infinity up to infinity. So the function domain for the logarithm is just the positive numbers, and the range is all the real numbers. Now if you look at the limits when x approaches infinity, then you see that the answer is infinity. When it approaches 0, the answer is negative infinity. And of course, the graph intersects the x-axis at x equal to 1. Okay, next, let's take an example where you have a base which is less than 1. Now the opposite happens. You have a function which is still defined on positive numbers, but it shoots up to infinity at 0 and goes down negative infinity the other side. So domain and range are just the same as before, but now the limits are the opposite. So when you approach infinity, you get negative infinity. When you approach 0, you get positive infinity. So that's the behavior of a logarithm whose base is less than 1. And finally, the plot has the same x-intercept at x equal to 1. Now, the point is that when you have inverse functions, then their graphs are reflections of each other in the line y equal to x. So for example, if you take e raised to x and log x, then they are inverse functions, and if you look at their graphs, then they are reflections of each other in the line y equal to x. And just the same happens if you take e to the negative x, and you see that again you have a reflection, but that's slightly harder to see. The red plot is reflected in the line y equal to x to give you the blue plot. Now, of course, there are lots of properties of the exponential function, and in just the same way you have properties of logarithm. So the logarithm of x times y is logarithm of x plus logarithm of y. But if you have quotients like x over y, then they turn into differences. And finally, if you have powers, then they turn into multiplications. So the log of x raised to b is b times the log of x. So the point is that logarithms are really useful because they convert multiplication to addition, they convert division to subtraction, and they convert powers to multiplication. Now, An important rule is the change of base, where if you have a base x, you can change to base a by this kind of a quotient. So the logarithm of y to the base x is the logarithm of y to the base a divided by the logarithm of x to the base a. Okay, so for example, when you get back this answer from solve, then that really is the logarithm of 5 to the base 2. Okay, so at long last we can talk about the derivatives and integrals of logarithm. So derivative of log x is just 1 over x. That's a very nice property, it's very surprising, but the fact is that logarithms grow more slowly than polynomials. Now, because we have a change of base formula, so you can work out the derivative of logarithm of x to the base a as 1 over x times logarithm of a. You can apply a chain rule and work out more complicated derivatives. And here is a plot of the logarithm and its derivative. But notice that the logarithm function is only defined for positive x, whereas its derivative is defined for all x. And that's an issue which we'll come back to later in the lesson. How about the integral of log? Well, the integral of log is x times logarithm x minus x. Now, that's a bit hard to prove, but you can check the answer by doing a derivative and you get back the original function. So the integral of the natural logarithm is x times logarithm of x minus x. So here is a plot of the integral. Okay, now an important application. So the integral of 1 over x is possible to compute, but for that you need to worry about the fact that the logarithm function is only defined for positive x, whereas 1 over x is defined for all x. And to overcome that difficulty, what we do is we introduce a logarithm of the absolute value of x. And now that's nicely defined for all numbers x, except of course 0. And once you've done that, then you can say that the integral of 1 over x is the logarithm of the absolute value of x, but in the Wolfram language, the log function can handle both positive and negative numbers. So for example, the log of negative 2 is log of 2 plus a complex number. And so in the Wolfram language, the integral of 1 over x is just log x. But in fact, one could write as logarithm of absolute of x plus c. Okay, so finally let's talk about an application. So here is an exponential decay function. The n over here is the quantity at time t equal to 0, and the question is how long would it take for the function to reach half of its initial value. Well, to do that, we solve the equation and you get back an answer, and this answer is called the half-life of the function. The lambda is called a decay constant. It tells you how fast it decays, and 1 over lambda is called the mean lifetime of the function. Now, often when you do such calculations, you will need to know the logarithm of 2, so the numerical value is approximately 0.693, and that's well worth memorizing. So with that, we come to the end of the lesson, the main point being that logarithms are very useful in solving exponential equations of this type. Now, just like you have properties of exponentials, you also have properties of logarithms. The derivative of logarithm of x is 1 over x. The integral is a lot harder. It is x times logarithm of x minus x plus c. The integral of 1 over x is the logarithm of absolute of x plus c. And of course, you can use logarithms to find the half-life of a function. So that's a brief introduction to logarithms, enough for us to now start talking about the so-called L'Hopital's rule, which we'll do next time. So I'll stop over here. Thank you very much.